Reducing atmospheric greenhouse gases like carbon dioxide, CO2, is the foremost way to combat climate change. This process, called carbon sequestration, involves the long-term capture and storage of CO2. In recent years, research in this field has led to the development of a new class of substances called porous liquids. Composed of porous solid frameworks dispersed in a bulky liquid medium, these porous liquids combine the solid-like property of porosity with a liquid-like ability to flow, thus allowing the retrofitting of these materials in flow processes. However, current progress in the field is limited only to the capture of CO2, not its consequent use. Keeping this in mind, researchers from the Department of Chemistry, Indian Institute of Technology, Bombay, India, have developed a new class of solvent-free porous liquid that not only traps CO2, but also converts it to the industrially relevant product calcium carbonate. They used polymer-coated hollow silica nanorods with bioconjugated carbonic anhydrase enzyme to create a composite porous liquid having a room temperature viscosity similar to that of honey. CO2 gas was purged in the composite liquid at room temperature and was captured by the hollow mesoporous silica nanorods. After the purging, CO2 slowly escaped out from the pores to be converted to bicarbonate ions by the carbonic anhydrase enzyme molecules present in the neighborhood. These bicarbonate ions subsequently reacted with pre-added calcium ions to form calcium carbonate crystals having calcite and aragonite polymorphic structures. The porous liquid could be reused after removing the crystals. The scientists could also freeze the entire system below -20 degrees Celsius to indefinitely store the CO2. In a clever experiment, they used two liquid droplets, one comprising of CO2 sequestered composite porous liquid and the other made of liquid polymer with calcium ions. These two droplets were connected through an interfacial channel. The bicarbonate ions formed in the first drop and the calcium ions present in the second drop diffused due to the concentration gradient and the liquid-like property of the material, resulting in calcium carbonate formation at the interface. This demonstrated the possibility of ion and molecular transport for deploying several kinds of reactions in the porous liquid, all of which are not possible in porous solids. This novel application of a porous liquid to convert sequestered CO2 into a commercially useful product creates new possibilities for industrial carbon capture, with the end goal of mitigating global warming.